Chapter 11, number 55. A disc-shaped merry-go-round of radius 2.63 meters and mass 155 kilograms rotates freely with an angular speed of 0.641 revs per second. A 59.4 kilogram person running tangential to the rim of the merry-go-round at 3.41 meters per second jumps onto its rim and holds on. Before jumping on the merry-go-round, the person was moving in the same direction as the merry-go-round. What is the final angular speed of the merry-go-round? So the key thing here being that all the torques are internal. They're caused by either the merry-go-round or the person, and so the angular momentum is conserved. The angular momentum of the merry-go-round at the start is, of course, just I omega naught, called I naught, plus there's also angular momentum in the person, which is m1 v1 r perpendicular. At the end, there's just angular momentum of the person and merry-go-round going at omega f, which is sort of what we want. A couple things. We need the moment arm of the linear momentum, which comes from the line of action of the linear momentum, and we can see that this is the moment arm, and therefore r perpendicular is just r. That's convenient. And so we have, it's a disk, so we have 1/2 the mass of the merry-go-round times its radius squared times omega naught. And we add m1 v1 r for the person. And then it equals, and we have both the disk plus, and now the person is essentially a point-like mass, and so we get mr squared for the person times omega f. So we can just solve for omega f. We get omega f is 1/2 mr squared omega naught plus m1 v1 r, and then we divide by 1/2 mr squared plus m1 r squared, and we get our answer, which turns out to be 2.84 radians per second. If you end up getting a different number, it might be because you have to convert the 0.641 revs per second into radians per second, because there are 2 pi radians per revolution. So remember that when you have the initial one, you have to do that before you can put it into omega naught.